Hi, everybody. What we have here is a deeper understanding. It's February 11, 2017. We have Frazzle, Cleef, and Joe, and we have really wonderful news to share with everybody. And it's all yours, Fraz.
Thank you very much. And basically, we're beginning into the circuitry. And there's a bunch of things that we need to talk about first in the line of how these systems work. You can look on the internet and you can look up the circuit called a Joule ringer. And we'll be having links at the end of this video to one of the better, easier to understand of the circuit, and then we'll get back into more detail in one of the future ones. But today we're going to begin why the Joule ringer works. The first picture that I'm going to bring up is a, oops, sorry, that didn't work. Hit the wrong button. To share photo. We've been talking on a couple of different topics in the background, and we realized that we needed to cut a few things. And this first, that one come up? Yeah, here it goes. The ferrite rod. In the Joule ringer circuit, there's a piece of ferrite. Ferrite meaning ferrous, ferric material, iron. It can be pieces of metal stapled together like your brushless fan motors. It can be a rod of a mixture of stuff that's ceramic. It can be pressed out of a paste into a form. Ferrite is, as I say, it's basically one of the properties of iron. The interesting thing about the ferrite core is that when there's a electrical current or a magnetic field placed next to it, it develops a magnetic field. And I'm using the classical definition of magnetic, meaning that when it's activated, it will latch onto another piece of steel, be it your refrigerator or a piece of steel metal or a nail or anything like that. And it's because of this activation property of the ferrite that it basically makes things more energetic on the coils that you wrap around it or through it or in it. And I'm being very general on that. In our first group, you'll see at the top of the upper left-hand side, and I'll just quickly draw a circle around it, that item. If the ferrite rod is glued into the middle of the coil, and it's got one wire on one end and one wire on the other, and they hit it with a DC current, the ferrite rod becomes magnetic in the classical sense. If the rod is loose and can slide back and forth, when you apply the field, the electrical current to it, the DC current to it, it becomes an actuator. The ferrite rod will slide forward and backwards in the field. It'll move. In the version that is not glued, where the ferrite rod can move, we have certain devices such as actuators, magnetic switches, magnetic reed switches, electromagnets that are big enough that you can pick up a car with them, as things that can work that way. We can go to the next thing, which is we actually move the two ends of the ferrite rod around. And in the case where it's sticking straight through, we have classical magnetic properties, the north and the south pole, north on one end, south on the other, with the windings in the middle. We can join those two ends together and make a loop out of it, or a ring. And we have our second example, which is that one right there. There's no difference in the first one to the second one, except the ferrite rod is now a ring. And what happens is there is a electrical charge or a magnetic charge or that goes in a circle, plasmatic field, in a circle in one direction through that rod, that ring. If it was an AC, then it would pulse back and forth if it was a true AC current, and it would work also. But have a different function than just the rod is just this circle ring that we've got with the simple wire. The next stage is the same ring. It's the one in the middle. We have the coil going all the way around the outside. What this does is it accentuates the rotation of the fields of the forces on the inside of that ferrite ring. Another interesting thing that we can do is put two circuits on it. You can have power, like the plus minus on the top, on one side, and you will get minus plus off the bottom. The ions, or the plasma field, or the magnetic field, take a choice, it's all kind of the same thing, it's forces, are still spinning through that ferrite ring. It works just like a train set. It picks up cargo on one side, and drops it off on the other. The interesting part is there's not a lot of drop in the amperage or voltage when you harvest from the other side of this ring. It says, well, where did you get the extra electrons or the extra force? Well, that plasma comes in as it's being drawn off. So that ring works kind of like an antenna. We go to the second group. On this one, we start with that ferrite rod, but we drill a hole in it. We make a donut out of it. We put our wire around the outside, which shows the plus and the minus, but the donut's hollow in the middle this time. So instead of having that solid ferrite rod in the middle, we have this washer, this donut in the middle. We can then slide a copper wire through the middle. The current that runs from the plus to the minus on the outside doesn't diminish as long as that's basically tumbling in a circuit. But we have usable power coming out the copper wire. Positive on one side, negative on the other. We go to the second group, which is that one right there. And all I've done is instead of having one of those donuts in place, I stack a whole bunch of them together. And then I wrap the coil around the outside and ping the outside coil, and the ring on the inside works even better. Why? We just have more surface area of ferrite to work with. The biggest difference between the plates welded together or stapled together on some of these circuits and the ones that have the ceramic ferrite core or rod or ring in them is that the composite has separated the microscopic or the atomic ferrite molecules apart. So the matrix that's holding it in the ceramic form is basically providing the distance between the particles so that the electrons can pass through and around and into it and activate it. It is a surface area to volume relationship. The ceramic ferrite rod or ring has millions of times more surface area because of this pushing apart of the pieces of ferrite in it compared to the steel or the iron buckled together. The differences are not even comparable when it does, but each one of these it does a little bit different in the circuitry, makes things work a little different in the field arrangements. That one. Go down. We can have, in this case, a single filament going through the middle, just like we did in the other examples. Or if we want to bump it up, increase the surface area of the wire going through the middle of it, we don't increase the diameter of the wire, because when the diameter of the wire increases, the surface to volume ratio decreases. It's inversely proportional. So we want to go with smaller wires, which have a greater surface area to volume, and then kick it up again by having more of them go through. So we can do multiple strands through the middle of this coil and get more pickup. It's just, you're just harvesting electrons, photons, plasma, you're just harvesting it as it's going through, and you need surface area. And so we have multiple strands. What's interesting, let's see, along this same line of reasoning, we can take the circuit that we started with, which was a ring, and we can do two circuits or multiple circuits and either have multiple take-on or pull-offs, or have multiple strands going through the middle, and each one of those strands can go to a different circuit. Okay? It doesn't matter. The power that you're using to generate the field is not affected by, or minorly affected by, the pull-off from the wires going through the middle of the ring. You're basically getting more out of, you're getting more work or more watts out of the system, for lack of a better term, with more circuits going through the middle of this ferrite ring. So we could actually clear this marriage those two ideas together, meaning that you could have multiple circuits for different things on the outside. I'm sorry. Multiple circuits on the outside of the ferrite ring doing either pickup or takeoff, or you can have more additional circuits spinning that ring, the plasma field on the inside of the ring, faster. These are all the variables we have to play with. So there's a lot of different combinations. How does this go into practicality? We had a comment from the guys that were doing building, I'm going to stop share on this one, of the car units, where the problem that we had was the connection between the wires of the car unit to the strand wire, especially going back to the transmission. And where we were having a problem was they were pulling apart. And so we needed a better connection. Let's see if I can see which one it is. Hopefully this is the right one. Strand wire does not fit the arm and plug and play very well. You can take, if you have the supply coming from, which would be, we would classify right now as the positive, going into the catcher's mitt of the, and if you basically use the solid wire as the catcher's mitt, then you could crimp down on the stranded wire. But going the other direction, trying to go from solid wire, which would be the plus end on the on the output on the solid wire, into the catcher's mitt made by the stranded wire, it doesn't stay very well. It causes a problem. And so Patrick has come up with a workaround that is quite ingenious, and it goes back to the wire rope connectors. And so we're using this electrical connection similar to how we would fix a steel cable or rope in a smooth splice. And so the ends are, and so basically what he proposes is that wire A and wire B, in this case both being strand, we expose about 3 centimeters of the strand wire. Splay it apart just a little bit, and then shove the 2 wires together, interlacing the fibers together. One of the interesting side notes of this type of connection is you can take 2 phone books and basically shuffle the 2 phone books together like you would a deck of cards, and then give a slight tap on the top and bottom where it is, and then grab the bindings of both books and try to pull them apart, and you're not going to be able to do it. The frictional force between the pieces of paper hold the 2 books together, and it's a tremendous amount of force. So in the case of what Patrick is suggesting, is that we shove these together, so there's at least 2 centimeters of each, and then give both wires a bit of a twist in opposite directions. And this will basically bind the 2 loosely together, and the nano coating and stuff will transfer from one to the other. Now, this was such a good idea that Patrick went one step further. He says, I don't like the idea or the notion that at the end of a wire, you can have plasma leakage. And now in one of the examples, how we could stop it, we did like this drawing I have on the right, this bend at the end, which sends the plasma, it would be coming out, heading towards the end, but then it'd loop back in and go into itself. Not a bad idea. The only problem is you still have a loose end sticking out, and you'll have a little bit of discharge from that plasmatic discharge at the end. At the microvolts that we'll be dealing with the dynamic core and the pickup antenna in the middle, is we cannot afford to be wasting that little bit of voltage and amperage right there at the beginning. We want to trap as much as we can. And so by doing this wire rope splice, it gets them together, but you still have these little tag ends sticking out. So you could have plasmatic discharge possibly at that. But he recommended, he says, with just logically thinking, if we take a piece of nano-coated aluminum foil and wrap around that joint, it would basically provide shielding. Now we take a look of our computer wires that are used for going to the printer, or coax cables that are shielded. There's actually a piece of aluminum foil wrapped around in the insulation that keeps outside RF interference from getting to those cables, especially the ones that are really, really sensitive, going to video drivers, and you know, that are where data has to be absolutely spot on. There can't be, you know, loose, you know, a wild charge or something running going through there. Those cables are shielded. So the next idea, as he was going down through his logic, which was just spot on, was that you could put a little bit of caustic, a little bit of GaNs underneath that aluminum foil, and then either tape it with electrical tape or shrink wrap it and seal it all in. So in addition to making a much better splice, you actually set up a little bit of a capacitance or a capacitor in line. So if you lose anything in that particular spot, it's sitting there ready for when the circuit needs that little bit more voltage or amperage. It's sitting there in reserve waiting for you. Okay, thank you, Patrick. This connection solves my biggest concern with my car unit, and being it that it's a four-wheel drive vehicle and I do run off-road, I don't like connections that fall apart and loose. And we don't really want to put a lot of pressure, and especially with dissimilar metals, over those connections. So in the line of all the other standard ways of connecting two wires together under the hood, I think what you're proposing is a very good workaround, and it's a very solid connection. You can actually put these two together, two wires together, put a little foil around them, put a little tape or shrink wrap, and you're basically not going to be able to pull them apart with, you know, 50, 60 pounds of pressure. Unless something, you know, it's a full pull, it's not going to come undone. It's going to be in the same tensile strength as the crimp connectors we use in the automotive industry to go from strand wire to a lug nut, lug bolt, bolt and lug connector in the circuitry. So I think this is a very good direction, especially as we move into more stranded wires with our electrical and our magravs and our car units. So thanks, Patrick. I like this workaround a lot. Stop share. Go to the next one. So we work with a bunch of different folks with different backgrounds and understanding of different systems, and we start getting aha moments with these new innovations and new ideas. So we have at the top of this Patrick's connection without the shrink wrap or the electrical. What would happen if we went back to the Joule ring or Ferrite rod or washer or donut that we were talking about earlier in this tape? Why not? Why can't we do a wrap like so? There's no reason for it. Now, in what most of us have found with the plasma batteries, pulling it off in the middle, if you just did a direct pull off, would be a minus. But that's just basically direction. When you look at the whole, what that whole piece of wire is doing wrapped around the middle, you've basically, this system is sucking in on the positive and pushing out on the negative, or whichever you want to go. We have a direction through the wire. So it's going to be positive or negative at one end or the other, simply because of what's happening with the wire going from A to B. So if A to B has got the load on it and is pushing current through it from the wire from A to B, then the left-hand side takeoff will be in reverse, will be the positive, as I've got marked, and the other end would be the negative. Cool stuff. So why don't we bump it up one? What would happen if we take Patrick's connector, and before we sealed it up, or we slid some ferrite donuts over the top of that aluminum foil, or put the aluminum foil over the top of the ferrite core, and then the wraps on top? Why not? Okay, this is some of the game changers of what we're going to be playing with in the next couple of weeks, is our understanding of what in the heck are we doing, and why is it working, and how is it working. A lot of it has to do with what happens when a plasmatic field comes in contact with the ferrite. Now, which one of our ganses is a ferrite? It's the, get my pen up there. It is the CH3 nano, which is the stuff on the bottom, gravitational. But you say, well, okay, but that's the stuff that the magnet sticks to. That's where the problem is going to have when we start mixing the nomenclature for magnets with the nomenclature for electricity, both AC and DC, and the nomenclature for plasma. I want folks to start thinking very strongly of moving to the words expansion or contraction, or expansion and implosion, which would be better. Where you expand on one side of the equation, you're pushing out, and on the other side, it's collapsing, it's imploding. You can use plus and minus, you can use red and blue, you can use gravitational magnetical, but what we're looking at is what is happening. Is it expanding? Is it pushing out? Is it becoming lighter? Is it is it moving away from the center? Or is it attracted to? Does it have a gravitational attraction to each other? And if we look at expansion and contraction, we're looking at, does it expand in the circuitry or does it collapse? Is it a step up transformer or a step down transformer? Does it make a bigger field or does it cause it to interact with another field? So direction, when it comes to plasmatic flow, is more important than in calling it some of these other things like magnetical, gravitational, plus, minus, that kind of stuff. We're really needing to get into this expansion and contraction, or expansion and implosion as terms. CH3NG, gravitational, is basically atomic size attractive particles. They attract to each other, they cling to each other, they gravitate towards each other. They're on the implosion side of the equation. It's getting tighter together. The CH3 which is that nano black stuff in the bottom, that you can put a magnet to and it'll move under the influence of a magnet. This is the ferrite that we're looking for. We can use it exclusively as a paste inside our systems, or we can mix it with other compounds. You can get it so it's with a gel, or you can mix it with something like plaster of Paris, cement, whatever, something. Basically, you're looking at something that will actively react to a plasmatic, magnetic, or electrical current and set up a field, set up a plasmatic field. And this is what the CH3NG does. And it does it extremely well because the surface area to volume is as much as you could possibly get. You can't ask for a better ferrite core than CH3NG. G. And this is why back 2 months ago, we started pushing nomenclature for Gans's. This was the first aha where we went, wait a minute, there's more going on with the Gans's than just, oh, it's CH3, oh, it's CuO, oh, it's CO2. We're graduating, we're going forward, and we're going to be playing with the different properties of each of these Gans's, because each of the properties, whether it's in the gaseous state or in the aqueous state or in the nanostate, you see the GAN, you're going to have slightly different things happening. Okay. Clear. So, stop share. And let's see. I think I'll see if I'm going to go back to my favorite example. This little device is a brushless motor. You've seen hundreds of them. They're commonplace. You have your copper wire coil. Oops. Sorry. I get it. Photo. Didn't mean to do a quick screen. Pen up. Go to, basically we come up, we have the coil, and it comes back down. One side's positive, one side's negative. If it's an AC current, then it runs both ways, back and forth, does different things. It's no big deal. It's just, it causes the field to pulse. Now, the next one, change color. The ferrite core is a donut, and it goes through the middle, like so. And this particular ferrite coil is a series of stacked steel plates that are basically riveted together. So the surface area to volume isn't all that great, but it's a durable piece of equipment. It's not really efficient because it doesn't use the better ferrites available, but it's cheap, easy to put together, and you get a lot of work and a lot of mileage out of the brushless motor, and it's simple. But anyway, the purple is the first part of the field. The ferrite core also continues up and around on the outside of the moving part of the motor. Now, the brushless motor has a series of pluses. It has sets up a magnetic field of north and south in a whole bunch of layers. If you take a look at it, there's probably anywhere from 8 to 48 separate fields that are side by side. This particular motor runs on AC, but it's only one leg. It's a 110. And so the circuit is actually a pulse DC that makes this motor run. And because it comes in on the same direction on the coil every time, it spins one direction. So it's a pulse that basically pulses around and through. And the change of the magnetic field, because of that pulse, the fan moves, and at one point it's oriented, being pushed by one negative pole and being attracted by the other positive pole. The momentum carries it into the next field during the pause in the 60 cycle and here in the United States, and in the pause in the 50 cycle in Australia. And the angular momentum of the spin causes it to go into the next set of fields. And when the coil pulses again, it attracts and pushes from a slightly different position in relationship to the route or the center of the motor here. And so you have a very efficient squirrel cage fan. And for those that have pulled apart squirrel cages, have seen them, this is all this is. It's just a simple motor, brushless motor that's running a squirrel cage blower fan. And I took this one out of a dishwasher. I've got one that looks just like it that basically inflates my greenhouse. There's another one that's inside your refrigerator freezer compartment that moves the air from the top, the freezing compartment of your refrigerator down into the refrigerator where you keep the milk. So you have the freezer at the top, getting really cold, and then the air pushing it down. Same motor, same circuit. The schematic on the left-hand side, the drawing, basically you've got your color. Your coil comes in, wraps around the ferrite core, and goes out. This sets up a charge that at first fills the inside loop. Once that's established, it sets up a secondary loop around the outside edge. This particular motor, you'll notice, has rounded edges, but it's square. The manufacturers have found that it's economically feasible to cut all their plates out of that, which comes out of flat sheet of metal, squarish in shape, and just round off the little bit of waste is the rounded corners. This motor would be even more efficient if it was a circle like that donut we showed earlier in this video. So they're sacrificing efficiency slightly to save in materials in building the motor. And you get into companies as large as, you know, Ford Motor Company or General Electric, any place that they can save 2 cents or 1 cent on each item is millions of dollars in the bottom line, because they put out so many of these. It's amazing what a few cents in savings does for the profitability of those corporations. This loop, inside its loop, is the basis for Alex's beads. Basically, he was using the plasma battery that was shorted out from the negative to the positive as the kicker for the loop. The first set of beads went around and attached back, and then the second set of beads went around the outside edge and attached back. So I'm saying this is the basics. This is a very, very primitive Joule ringer circuit. And it builds on the idea that the first circle gets charged up to capacity, and then the second one builds up. And if there's a bleed off in the system someplace, this thing keeps running. The circuit stops when there's no charge. It stops when it's fully filled. So as long as there's someplace bleeding off plasma, using it as work, this thing keeps working. Okay, stop this one. Okay, I'm going to pause the presentation for a minute and bring in Cleve and Joe and do a little comment. Cleve, you want to start? I see you unmuted first.
Oh. Gee, that was a mistake, wasn't it? I haven't got anything to add. Other than, you know, I really appreciate the lengths you go to explain this stuff, because I'm a dumb monkey, and I don't understand electrics too well at all. And to have someone explain all this as a basic thing is really handy for me. And I feel that this is a key part of it all, and understanding it is allowing me to understand the way that the whole thing fits together. So when I'm building it with that knowledge, I can expect the thing to work. And I do thank you. Over to Joseph.
Okay, we'll pass the ball to Joe. Joe's been really coaching me for the last 2 months on this circuit, and as we say, if I can get taught it, then I can teach it to everybody else. Everybody else should be able to get it. I'm the dummy of this group. So, Joe, what do you have? Do you have any comments at this point? We lose Joe. What I think. Uh-oh. Or did I lose my...
Oh, I done muted. He may be getting snowed in.
Yeah, it could be. Okay.
Oh, here he is.
But he's not getting he doesn't have a mic.
Can you hear me?
Yeah, now I can.
Okay, so take the training wheels off and let it loose. Show the second half of it.
Okay, shall we start a second video, or should we just go forward?
Roll. Let it rip so
Let
they
it
can
roll.
understand it.
Okay.
I'm going to kill the camera so I can get bandwidth. Ready? All right.
Okay. Onward. This is getting into the edge of my knowledge, and so we'll see what we can do here. It's going to take a second to bring up these next series of drawings. Which one do I want to start out with first? Probably the one that is sitting over the top of the shop. See, that's going to be a little bit further down. And we're going to go with a basic Joule ringer circuit. Find it. Hold in there, stay with me. This is going to be one of those, take a moment to look at it and then go on to the others. But it's an important drawing, and we use it all. As I say, it's way back in the beginnings of our talks, and it's the one that we screw up time and time and time and time again. Car units. I grab units. There's some clear back in December. I want to get almost to November, my backlog of drawings. Here it is. This is on, I have this actually posted on my wall. And it says, fellow humans, why do we sabotage this circuit every time when we get to this point? It really isn't any more difficult than this simple circuit. You have a Ferrite core. You have on one side a set of coils, another side another coils. In the Tesla stuff that I worked with back in 2000, basically it was your primary and secondary coils. We use them to step up voltage. We use them to step down voltage. When we use them to step up voltage, amperage goes down inversely. So pretty soon we can get from low voltage to high voltage and almost 0 amps. And how we play with the circuit tells us what we get out of it. So once again, fellow humans, why do we sabotage ourselves with this circuit every time we get to this point? Okay. It is a simple circuit. It's a loop. It's a loop circuit inside a loop circuit. it. There is nothing else to it. It's that simple. But there is hundreds of patents that basically spin this around, orientate it a little bit differently. The patents are actually for different uses of this circuit. The original patent is one of Nikolai Tesla's. It's everybody else finding another application. This circuit is your brushless motor. This circuit is your actuator that turns on and off a switch when a current goes through it. It activates that electromagnetic rod and turns on the switch, turns it off. It is your step up, step down coil. It is the transformer that makes your doorbell work. Okay? It's used over and over and over again, but for some reason, it's not taught why it works or how it works. In the next bit, we're going to see what we can do to eliminate some of the misconceptions. Okay. Stop share. That's a little bit too far. Grab another image. So we take a look at the basis of this coil. It's not a new circuit. At the bottom, you have your power supply. And this one says high voltage DC. Goes into the middle. It's plus on one side, minus on the outside. On the inside is a solid copper wire. Goes out and around and back. That's your primary core. Your secondary coil is on the outside. So what we're looking at is on the inside of this coil, you have the primary coil of solid wire in the middle. It just kind of dangles in there in most cases. The current comes in and it forms a field that pushes out, an expansion field, expanding. It is collected by the secondary coil and is basically contracted. It's being condensed, imploded into the secondary coil. How well does it do? It depends on how many wraps is on the outside. It is the ratio from the inside to the outside, what you get. The spaces between the wraps on the coils is what we were talking about. And so each time you add one more coil, that is adding one more to the multiplier. So that if this one, let's say there was 128 coils on the outside ring, their multiplier factor would be 127 times whatever the voltage would have been off the center high voltage. Pretty cool stuff. Okay, stop share. But this is an old patent, probably 1880. We take a look at our MagRav units, and there is a spring inside a spring. If we take a look at what Sandor did with his magic trick, he basically showed you how to expand and put a little more separation on your ring, and he only had one wrap on the inside. Basically what you're looking at right here. This is some of Tesla's work. Stop sharing, go to the next patent. It'll take me a minute to bring it up. Hopefully hit the right button. Once again, a really old patent. This one's showing what looks like 4 circuits on a ring. It looks like 4 coils on the ring. What you're doing is you're causing the plasmatic field to race around the inside of that. And instead of having 1 coil, this one has several. And I'll just keep drawing them, because I want you to kind of get your mind wrapped around this. There's another one, it's a different circuit. And let's see, one more color. Okay. If you pulsed each one of those coils slightly out of phase, and you only have to have 2 cycles to do it, slightly out of cycle, the one at this point and the one at that one could fire at one moment, and then this one on the other side and that one across can fire at the other moment. And it'll cause a rotation on the inside. But it also sets up a plasmatic in the 2-dimension rotation inside. And we can demonstrate that by affixing a magnet on the middle, in the middle, on a shaft that has a, change colors, north on one side and the south on the other. A simple pulsating DC current, which is what your 110 AC is, causes this rotation, plasmatic rotation, to occur not only inside the ferrite ring that's housed by this series of cores, but it causes a spin on the inside of the toroid. In the inside, there's a toroidal spin, and this is how your electric motors, brushless motors, operate. It's slightly out of phase, pulsing AC current, which is pulsing DC actually. So your AC current is a pulsing DC at this application. And a simple capacitors or a simple delay so that it takes a different amount of speed time to go through one part of the circuit compared to the other. I'm talking about this Joule ringer circuit. The time it takes to go through one cycle of the little ring compared to one cycle on the big ring. And when that comes back in, you'll have a change in when it pulses inside, because you've got one on one side and one going on the inside. It's going to cause a change in the north-south magnetic field inside that circuit. Clear all. Get rid of that one. Remember, keep an eye out for this drawing. You'll see this come up time and time again. Nothing new. This is some of Tesla's work, 1880. We're going into some really old archives. Let me stop share. Pull up the next one. Blueprints up. Okay. There's the patent number. There's the date, 1888. Okay. The reason why your MagRav units work, why your car units work, is this circuit right here. Okay. It's part of the forgotten knowledge, the stuff that people haven't understand, but it's something that we're all just coming on to learning right now. And those of you that are watching this video are right up there with us as we understand how this works. You can have this circuit can be set up that it's basically 4 plasma batteries in a circle. We've seen that design, or single plasma battery in a circle. We've seen that design. This can be a series of ferrite coils with a coil of ferrite cores with a coil on the outside. This can be just a simple wire on the inside and copper coils on the outside. It has to do with the intensity of the plasmatic field that's being generated. Okay? This particular one probably will throw a 4-vein or 4-circuit plasmatic field. I don't have a 4, but I'll have one. I'll show you one that what I'm talking about. Stop share. Let's bring up a multiple field. Now, those of you who have seen my flight engine is that is a single field. It's not a multiple field. That was the realization that we probably needed to do a little bit more work on the design, but we had to build the first one to see what we were dealing with. Yeah, going back to history. This is what we're talking about. This one, if we count the blue rings, you'll see that it's actually 4 circuits. If you count the green ones, it's 4 circuits, or 3 circuits. If you count the red ones, they're 3 circuits. So if you wanted to have it with the 4 fields, you'd be basically adding 1 more into this toroid. The reason I'm bringing this one up is this, because of the rodent people have done all the mathematics and stuff and really worked this stuff out through observation and testing. In their wire models of the rodent coil, they realized that the toroid field that formed above it was mathematically represented in this shape. The angular rotation is built in because of the way it can, like candy canes, into that toroid. So you're going to get rotation around the outside equator because it actually snakes its way in, it swirls its way in and forms almost a tornado, an implosion in the middle, an implosion, a collapse, a condensing in the middle. Expansion on the outside, collapsing on the inside. Not only is there one coming in, I do it in blue because we're calling it gravitational, but there's one for the rest of you guys that know about it, is the field that comes out from the center, which is the expansion, magnetical expansion, getting bigger. And that is observed out on the perimeter. We can rotate this, we can speed up this spin, both in from the outside to the inside rotation, like this, basically this never-ending self-swirling donut that the inside becomes the outside becomes the inside. but we can influence the entire rate that the whole thing spins on the equator on that flat plane. The interesting thing is we can either do the field interactions on the outside, on the +1, +2, or we can do them on the inside, on the +1, +2. If we stack one of these fields on top of the other, we start running on these numbers that are coming across. And there is a frequency ratio that is like multiplying 9 times 9 times 9 times 9 because those are being hit all the time. Or the 2, 3, 4, 6, 9 progression. It's not quite as great. Or the 1, 2, 3, 4, 5, 1, 2, 4, 5, 7, 8, 5, which isn't as fast either. So there is lines in the mathematics, depending on which part is interacting, what you get out of it in the multiplication. But we're looking at basically setting up these toroidal, moving toroidal fields with the circuitry of the Joule ringer. Clear and end. Stop share. Locking up. Stop share. Go into the next patent. Go to next. Loading. Find it right away. Grab one of the others. Move on. Sorry about that. A second to bring these up. Those of you who have been working with the Tesla coils, you notice this circuit. It probably is going to let me hold it, expand it. But what we're dealing with is a primary coil, right there, and a secondary coil. In the case of, which is, remember, you got your primary and your secondary. We start with a little one and we ping the bigger one. In the case of the Tesla coil, we put a small DC charge at this end. You have a coil interaction of one coil pinging the next one here. There's a spark gap and resistors to keep the circuit tumbling in the direction that we want it. It gets to the secondary systems of the passive transformer, goes to the primary and secondary of the actual Tesla coil. You have the little one pinging the big one, which is sitting on this, looks like an antenna. The circuit has a ground at the bottom of the antenna. This takes your ground charge, we'll call it the negative charge, goes into the ground, the earth ground. And the positive charge goes up into the top, into that big silver dome at the top of the Tesla coils that shoots sparks out. All of us love and enjoy. The circuit works both directions. You can fire it from a charge on the left-hand side. Put a charge in this way and get lightning. expansion, lightning, expansion, out the top of the antenna. Part of the field is stripped off and goes to ground. When this at the top fills up, like a great big capacitor, gets to complete fill, there is an electrical discharge, high voltage discharge, expansion, because what those ions, what those charges are trying to do is either find their way to ground or find their way to the sky. Doesn't matter. It's heading one place or the other. And you're looking at, from a small start at one end, and we were using 1.5 volts, kicking out thousands and thousands of volts and high voltage out of the top. Simple circuit. This is a step-up transformer. We can work it the other way as it sits. We can harvest the electrons, static electricity, from the outside under the implosion. That was the explosion side of the expanding explosion side of the equation. We're going to talk about the implosion side, the collection of it. This works like a receiving antenna for your ham radio, your FM, AM radios. Basically is the same looking circuit where you have an antenna. It's got a certain length of wire on it. The longer the wire, the higher off the ground, the more voltage you can collect. And it wants to go to ground. So as it goes by, that becomes your primary. So we're working backwards now. Your secondary is your pickup coil, which is the little one on there. If you made that one bigger, it'd be more efficient in that case. And it backward charges the system. It'll actually tumble in the same way as it did the first time. At the far end, without doing any difference, you're going to have a maximum of about 1.5 volts. Because you're running the circuit, you haven't changed any of the circuitry on the inside. So what was in that direction was a step-up transformer that increased the voltage. You are now reversing it and bringing it in and decreasing the voltage. It's the only reason it doesn't work well backwards. Is the guy that was funding the Tesla coil that I was basically looking over everybody else's shoulders on when I said, I think we're running this thing backwards. He says, Raz, I am not spending $4,000 for a 1.5 battery charger. End of discussion. Didn't know any better. Went, okay, I understand what you're saying. And basically dropped that whole notion for 16 years. What we're looking at here is, instead of putting it backwards like we're showing in step-down transformers, we flip that part of the circuit 90 degrees. So now, instead of being a step-down transformer in that direction, we make it a step-up transformer, increasing the voltage, because we start with very low voltage, maybe 0.05, and start bumping it up. The technology is exactly the same. Not changing anything. We're just flipping the Joule ringer circuit that is in the middle. Clear. Stop share. Go to the next patent. Okay. As you can see, we've had a lot of fun with this. Where's my TP? Ah, there it is. This is it. That's all there is. Simple, simple circuit. This is an LC. On the left-hand side, you've got your coil. On the right-hand side, you have your capacitor. Everything works on this circuit. This is half of the Joule. Piece of cake. Time and time again. We look at this. Another photograph. Second here while I see which one I can grab next. Okay. There it is. This is the antenna at the top, picking up the signal from the atmosphere. It comes down, goes through two capacitors at the top. Draw some colors. This is your antenna at the top. You have two capacitors, one on each side coming down, and you split the circuit. Why? Because it's AC, up and down in the antenna circuit. Clear. We set up little gate valves in the circuitry. Okay? Just like in water. It can only travel one direction. So if it comes out of this side, let's say that one's negative coming in, then it comes out that side, goes round, it can only go this direction and goes that way. Ah. Guess what? That wasn't negative, was it? It was positive. Ends up being positive over here. Clear everything. Okay, the other side must have been negative, right? So we go that direction. It comes around. It can't make a left-hand turn because the gate valve's there. And it comes out positive again. Wait a minute. We started with an AC. We were supposed to have a DC, aren't we? That's the beauty of this circuit. This one goes that way, or it could go that way. But because there's a capacitor in the middle, it forms a pulse. Heading to positive. Well, where does our negative come from? Down here. It's just an open wire. Comes in. If it ever gets up in there, oops, it too would end up being a positive. It can try to go the other way, but it's, it can go to ground, but it can't, or go that way to ground. You can hook up your electronics to these. One is the negative, one's the positive, and it's going to work because it is basically being pulsed. Fan, an LED. If your voltage is high enough, it's going to work. Let's clear this and take a look. What are we looking at in this circuit? We're basically looking at a square and a square. You're back at your Joule ringer circuit. On this one, we're picking it off here and here to run to our appliances, but it's actually being pinged over on this side. Ground in the middle. Simple, simple, simple. It's the same circuit over and over and over again. Where you tap off of it gives you the difference from one spot to the other. Clear. What's the next drawing? I took a look at Douglas's circuit back quite a few years ago. No, not years ago. It seems like years ago. It was about 7, 8 months. And I drew it, what I called the V22, and submitted it to the foundation for consideration, at least for explanation of where to start to look to get, you know, for trying to solve, go to solid state. It's going to take me a minute to pull this one up because it's way down in the history books. In the files, way back. This tablet doesn't let me go through quickly. I have to pull it as we go. And I've showed my V22.2 drawing a few times in the last 2 months. And we're going to show a new way of looking at it, so it kind of makes a little more sense to folks. Almost there. Find it. V22. Come on. Takes a minute. Ah, V22. I laid this out to explain Douglas's circuit simply by standard electrical. What happens is you have in this the Joule ringer. You have one circuit on the outside, it looks like this. You have another circle on the inside that looks like that. In this case, our magravs are at the bottom. In the case of Douglas, he set up another circuit over here on the side, which was the starter circuit. And it had the pump. It had the motor that drove the pump backwards. It had an inverter to give the electric motor a false AC current in it. But that was his circuit. His power takeoff for electricity was about over here. It went over to 1, and this was his plug strip. You only had one plug strip on it. You had a fan on it and an LED. The fan, when it's running on this circuit, sets up a pulse because it's a brushless motor. It's running in the proper direction in the pulse. It sets up the 60 cycle pulse. Everything else, when we take a look at these, that right there, that's just a capacitor, and that's with the new nomenclature for our plasma capacitors. The nice part about it is it shows us direction of flow. You have the charge coming in to be transferred, and it goes into the catcher's mitt on the Armin connection, and it goes on. Goes that direction. When you look at a plasma circuit, you see these in place. You've got one there. You've got 4 on this side. You've got 1 there. Comes down, it feeds these 3 that direction. Comes around, feeds that 1. This whole circuit comes around and feeds that one because the other one's full, which comes back and feeds those 3, which comes around and feeds that loop. And in the case of Douglas's, where he had the other one sitting there, he had basically either a battery or an alternate. It basically was charging the starter circuit, and when it was up and tumbling, no longer needed it. So we could actually erase that whole part of the circuit out of the solid state. Looks like a mess. But what I'm saying is that is your Joule ringer circuit. At first, we couldn't figure out what the magravs did. They're basically your primary and secondary step-up coils, and they send out a plasmatic field. You could add more plasmatic field by running with the discharge from those magravs. And I have suggested that we use that shape to designate stacker magravs for plasma circuits. It's just a quick, they're just loops inside of loops, just a quick representation of magravs, and especially a triple stacker. Or it could be the V system. If it comes in and goes into an antenna, and you want it to broadcast on the inside of your plasmatic field, it just goes past your transmission antenna. Your magravs are going to do a lot of that themselves just by their design. They're going to be a transmitting plasma antenna. They're going to transmit anyway. But you could add actually another antenna on the inside field. This would be like either on the inside of your spaceship or the inside of your house. That would be the parameters of your fields that you were trying to establish, be it inside your house or be it inside your spaceship. We realized with Douglas's success here and with what Mr. Kesh said that he was going to need a second set of plugs. The first set that he had in basically keeps the Joule ringer circuit tumbling, keeps everything in motion. That's the primary that drives the secondary. Where you tap off for the second one makes a difference on how much voltage you're going to get. So basically, the closer you get to your maggrav discharge on one side and closer to the take-up of the capacitors on the quote, negative side of it, the more difference you're going to have in the amperage and the voltage of the circuit. So where you tap off of it is going to make a difference. The system goes to ground in several places. This is the part of the bleed off that makes the system work, because as long as it's not fully balanced, or if it's not full, if it's filling, it's going to be tumbling, it's going to be working. If there's no power coming in, the system doesn't work and it shuts off. So you have an upper and a lower limit to the circuit. And once it stops tumbling, you're going to have to do something to get it going again. It's going to take input. It's going to take the little kickstart that you see. The antenna has a source to ground on one side, and that one has an earth ground for this example. The transmitting antenna that's on the inside of the spaceship or the inside of the home can have a artificial ground. It can have lead GANs at the bottom. It doesn't have to be attached to the ground. Works fine. Your plug-ins at the far end have to have a ground, and that has to be an earth ground for earth-based structures. Keeps things from moving around. That earth-based ground basically says the plasma is going to come in from the antenna, it's going to do through your primary, it's going to go through your secondary, and you're going to bleed off a little bit from what you're using on demand, is going to go to earth ground, and it's going to keep harvesting out of the circuit that it causes the implosion from the antenna to fill the vacuum on the inside. Implosion. The wireless system, which is set up outside this thing, for this example, it is inside your house or your spaceship. It's inside the bubble. It's primarily going to be receiving from the transmitter the information. So you have expansion here on the transmitter, and you have a collapse of the field on the antenna. That one has a lead GANs ground to make it safe, because it's still inside the spaceship. It's still inside the home. if you've got a step-up transformer, like a maggrav, basically a Joule ringer circuit that is primary, pings the secondary, and boosts the amperage, you're going to have a pulse from the transmitter because of your electric motor at the top that's running the circuit, plus the magnification of the capacitors as they're firing. You're going to have a pulse discharge out of that inside antenna. So this is receiving a pulse, bringing it down, going through the step-up transformer, which could be a single stacker maggrav. It may be a full maggrav, don't know. Haven't gotten that far. There probably is going to have some capacitors in line, and one that basically keeps the power from going directly to ground runaway. So the discharge, the neutral or the ground wires are going to, is going to go to an earth ground, and that earth ground cannot be attached to the house ground if it has a grid signal, a 60 cycle or a 50 cycle to it. And it's like, well, why can't we hook it to that? It sounds like a really good place to put that ground to. The problem is, both for that earth ground and that earth ground, if we have your electrical panel, you have the two hot leads coming in, which makes your, in the United States, 220. They come in on both sides of the panel. You have a third wire, which is basically a neutral, and that one rides back to the pole. It usually goes straight to ground. It's just a safety one. It really, most of the old circuits didn't even have it. That's fairly new for US code to have it bonded back to the pole on the neutral. But you have a hot lead of 110 on one side, you have a hot lead on the other side at 110. The two leads are out of phase with each other. So when one is pulsing, the other isn't. And when the other is pulsing, the other side is resting. The result is, when we look at our breaker boxes, the breaker sits on it, we take the hot lead and run that out to an appliance. Let's say it's a fan. It comes back on the neutral wire, back to the breaker box. That goes to a separate bus, a separate piece of, basically it's aluminum in most of them, but it's a place for everything to bind to. That neutral goes to ground. Your wire, for the most part, the current is going to be traveling from the breaker box to ground. It's okay, no problems. Not only does your neutral bond to that wire in your breaker box, your ground wire, that middle wire in your appliances, and it's green or bare copper, that comes from your appliance. You see it go right down the middle, as I'm coming down through the middle, but it attaches to the same bus. So we have two hot buses in the electrical panel that your breakers are, one for 110, one for the other. Another one there. For 110, they take one lead off and run it through the circuit like the one I showed on the right. If it's a 220 item, like your hot water tank or your oven burners inside your electric range, they will take a hot lead from the left side and the right side, and the two wires come together, and you don't have it going back on the neutral. It just pushes back and forth on the cycles. You're not bleeding off for 220 as much. Your ground for your 220 appliances, your stove and your hot water tank, actually bond to the outside of the appliance. So the neutral, look at green, the neutral wire, which would be the green or the bare copper, bonds to the outside of your electrical appliances for North America and I believe most of the world if you have a grounded circuit. What happens is now both the ground and the neutral go to the earth ground on your grounding rod, and that's usually a 3-meter long rod feed into the ground so it gets deep enough that it comes in contact with the moist soil, makes the connection. All wire has a capacitance. It'll hold a charge by itself. You've done this when you've tested your maggrav coils, and you put a meter on it and it shows voltage and then it discharges and you don't have any. That's temporary capacitance inside the wire. The longer the wire, the more capacitance, the more ability to hold a capacity of a charge, plasma or electrical, that particular wire has. If your earth ground is corroded, or the ground is dry, or the surge coming down from the electrical panel is greater than what the earth ground can handle at that moment, and it only has to be just a fraction of a second, like 1/60th of a second. You have a little bit of backward pressure. If you had another wire, let's say it was coming from this device over here on the left-hand side, if that came to that same earth ground, you would have back pressure in that wire from your grid. So in fact, even though the line coming from the breaker panel going to earth is a direct charge, it's going one direction, it's a DC charge, the back pressure in anything else that you attach to that earth ground sets up an AC, which means not only can you get zapped from your electrical panel, from the grid, by doing that trick, you can get an earth charge coming backwards on a rebound from the planet into this wire. So attaching your maggrav units or your free energy devices or anything like that to a earth ground that is bonded to the grid, that is attached to the grid, is really bad news. And I highly recommend you do not do that. It's easier to basically go get another 3-meter rod and drive it in the ground someplace, and that way it's safer. So I took a look at this particular drawing, and it looks really, really confusing when we start to explain it as a Joule ringer circuit, even though it really is only that shape. Erase all. Going to another drawing. This is some of the new stuff for today that I was going over with several of our teammates. And I said, how can we depict this circuit in a way that makes it look more like Joule ringer circuits? So I separated out the different ones and realized I was dealing with more than the simple Joule ringer shape. We actually have one inside of another, inside of another, inside of another. Each one of these spots that I've got marked Joule is basically a possibility of increasing or decreasing the voltage in the circuit. So it builds it up or takes it down. That's why you have so many different places that will give you different charges. Basically, it's the difference from the current in one side of the circuit compared to the potential difference in the current in the circuit in another place of the circuit. I'll get it straight yet. But anyway, once again, you have your antenna goes to ground. It's an earth ground. Over here, your electrical goes to an earth ground. Comes in, goes around. So me go grab another photo. Stop share. Photo. All I did was highlight these different parts of the circuit. Basically, you're adding and subtracting. Each of those spots where you see Joule highlighted is basically the same as setting up a coil like that. There's one there, another one there, another one there, another one there. It sets up a field like so to that one. This one has one that goes to there. But we're setting up basically more and more interactions using the Joule ringer circuit. We're just putting it on steroids. We're just making it actually do something more than light a little LED. Not sure. I don't know if I've got anything more. Take a look real quick. And yeah, and there's one more. And just to kind of wet your whistle, this particular patent is before 1930. Looks kind of familiar, doesn't it, now? We've gone through with the different ones. This one is basically one, color some, 1, 2, 3, 4, 5, 6, 7, 8 Joule ringer circuits. Step up, step down type stuff in the part of the circuitry. Clear. There is a outer coil. I don't know if you noticed, there's an inner coil. Look familiar, folks? It's your platter. That's your mag graph. That is just a different application of the same circuit. This one happens to be, I mean, where my notes are. That one is known as, I have it? I could have it. Oh, do I have my notes here? Oh. Anyway, this is a lift drive. After we got through with our blueprints and our own, how do we get around and how we get the toroids to produce lift, we came up with this idea. This is what we thought we had. So once you come up with a solution, then you go see if there's anything else available in the known patents that describes your device, your new device, in a way that's similar. You know, did you discover something new, or did you rediscover something that was forgotten or hidden? Guess what? None of the stuff that we're doing is patentable because it's already out there. It's right there in front of you. And I'll show you our lift engine. It hasn't been tested yet. We're still working on getting it wired up. It's not easy. It's a little complicated. The mock-up, that last one I showed you, is that device. We were quite surprised to find a pre-1930 patent for electromagnetic lift engine that was almost identical to our Starship engine. We're still working on it. This happens to be a single circuit, and as soon as we got it together, realized that we probably, for stability purposes, want to go to a triple or a quad, like that first drawing I showed you of Tesla's. The first coil that had 4 circuits. This one only has 1. But we had to build this one to visualize what we were seeing in our drawings when we started taking apart the different circuits, and what Douglas had did, what Alex had did, what Mr. Cash talked about in how do you get lift, what the car units do. So anyway, I'm going to turn this over for a minute to Joe and Cleve and let you comment.
I don't even know what to say. All right, Cleve, gotta back me up here. Unmute your mic. What Frazzle's heading towards here is what he's heading towards here is that we have really discovered. Well, go ahead and take it over. I was just going to say that we rediscovered a lot of stuff, and we're really understanding Nikola Tesla's work finally. 125 to 130 years later, where actually the monkeys finally understood what he actually was laying out for us. Well, the general public is, they've been dealing in his work for this 100-something years and using it for other applications. I'll give it back to you, Fraz.
Exactly. What we're looking at is rediscovery of old technology. They're between the work of Schauberger and Tesla. As they say, Schauberger was the genius of water, that Tesla was a genius of electricity and plasma. The two individuals, from what we're discovering and learning, were looking at plasma fields and not realizing it. The similarities in the drawings that the two have, one working with water and one working with electricity, are amazingly similar, even though they were half a planet apart and they didn't have the ability to communicate like you and I do over the internet now today. These two individuals basically had an unbelievable understanding of plasmatic forces. Now, they spent many, 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 many years at it. We have the joy of the internet, and in the few months that I've been working on this circuit and trying to understand how it works, is a very short period of time. And when the team came together in November, each of us bringing forward a little bit of knowledge. Each, as I say, each one of us had the apple seed in our hand. You know, we have this one really good idea, pretty apples, you know, but we get it in our hand. The problem is, most of the time that apple seed, for all of us, is at the bottom of the jar. And we'll reach in and we'll grab a hold of it. We'll know that we got something really, really important, that we understand something. But the problem is, we can't get it out of the jar if we hang on to it tight and not share it. If you let loose of the apple seed that's in the jar, you know it's there, it's not going anywhere. You've already identified it, you've figured it out, you know that it's really, really important. You pour it out in your hand, out in the open, and you share. Because that apple seed, when planted, will grow into a tree and bear fruit. This happens to be a nut. You plant it, it'll grow into a tree, and it's a lot of nuts, a lot of stuff. You leave it in the jar, you leave it crammed up, not released, not open source. It doesn't go anywhere. It sits in the patent office forever, hundreds of years. You've got a piece of the puzzle, each and every one of you. We've got a piece of the puzzle. As we figure out what our little piece of the puzzle is, it is our goal as the Plasma Frontier team to share it with you like we did today. If what we present sparks an understanding of you in your heart and your mind of what you've got in that little apple that you have, please share with others. You know, share with us, it'd be great, but share with others. Open source it. This stuff has been hidden for over 100 years, and there's no reason for it. And there's a lot of you who have been working on this for many, many more years than our team has. If you've got a thought, write it down, post it. We scour the internet daily. Facebook, Google. Some of us are pretty damn good at searching white papers where we actually go into the patent office, open files, and bring up the white pages. This is what you're seeing. A lot of the others of you out there have been doing similar research. There is a demand, there's a need throughout this planet for renewable, inexpensive energy. It's going to be not one person that it's going to fall onto. It's going to be teams of individuals, teams putting together the information. It's kind of like our team, Plasma Frontier. You know, we're not the brightest ones on the planet, but we talk with each other. And if each and one of you puts together a team of people like-minded, puts in effort, puts in the work, builds devices, troubleshoots them, takes a look to see what's working, what isn't working, you're going to move ahead faster. And you're going to move ahead faster with information that we give you. And what happens is you will find things that we missed. You'll find things that we didn't even think about. And you'll come back, hey, look, this is great. And we'll, oh, wow, we've beaten our head against the wall for 6 months, a year, 5, 10 years, and didn't see that. So take a look at your stuff. Take a look at that little nugget of information that you've got that you figured out. Does it fit with what we're presenting? Does it help explain what we're presenting? Does your piece of information make it easier for us to understand the next one, which is like, how in the heck do we get these units to put out enough oomph to do something, to do some work? So the information is there. It's out on the internet. It's open source. We'll keep plugging the best we can, and we certainly appreciate the help from the individuals that have contacted us the last couple of weeks. This is the reason why this particular video is being put out so soon, is to thank you guys. And it made a big difference in the way we were thinking and going into the next step, which is the generators. There's quite a few pieces that we're going to have to work on R&D and develop. One of them is going to be capacitors. The next one is part of the Joule ringer circuit. And instead of, as I said, instead of the ones that where I showed all the wires going to each other, I started doing it in boxes. And that's one way of visualizing that you really aren't working with a direct plasma or direct electrical current from one side of the device to the other. You have your idler circuit, which is basically your tumbler circuit that keeps the plasma rolling. And then you have your harvester coils on the side that actually are picking up all this extra field of plasma or electrons and collapsing that into your electrical to make it work. And Joe's got a really interesting toy that he's been playing with, and it's a little more advanced than what I'm working with. So, Joe, you want to talk with what you got in your hand there?
Yeah, all you have to do is go look up Nikola Tesla's TPU. It's a toroidal power unit. And that's basically what we're playing with. And that's all these circuits that we keep using, the Joule ringer, the Joule thief, the tank circuit. It's all going back to this. What you're doing, you're going to harvest the plasma, ether, resonance, whatever you want to call it. We're very close. I can tell you that right now. We're very close. And this is where, you have to start using your imagination, where you have to look into things deeper. There's a lot of information out there, like Frazzle says, but like you said, we research so much. We're going constantly. We don't even have time sometimes to even talk. We just pass the research to one another, and it's there. We're close. We need a lot more help. We need at least another 50 eyes on this, and looking at it 50 different directions. That's what we really need. It's anytime one of us are going to crack this. Believe me, we're so close in understanding this now. I understand more about Tesla now than I did 6 years ago when I was really trying to figure him out deeply. It's amazing how much knowledge came out so quick between us. So, in fact, today, the conversation we had, we both catapulted, at least 2 years faster, would you say?
Yeah,
Rather?
easily, because I've been beating my head against the wall trying to figure out why that little fan motor was working as a Joule ringer circuit. And then I'm like, oh yeah, the printed circuit is the Ferrite car. That's the printed circuit. It's all right there as one piece. Doesn't have to be complicated.
It's just like this is the same thing as a core in the center, as wire wrapped, the second core, and it then has the wrap on the outside. It's the same as the Magrev coil. It's all the same. All the coils you showed, it's the same thing. And it just took me a long time to understand setting the pulse up and playing with it. I mean, I had millions of failures. I had successes. Now, here's the joke. The coil I just held in my hand, here's the same thing. This is a working model. Now, we're going to pulse with wave modulation. We're going to tune it. Now, we're tuning it. Let's tune it some more. We're going to tune it again. We have control over this. It is the same circuit. And it goes to show you that it is in production. It's been used for hundreds of years. And it's a way like you should. When you showed the Tesla coil backwards, it works. You know it works because when you're shooting a negative off the ground up and grabbing the positive, it's attracting the positive in, it's bringing the energy in. That's why if you look at our system that we showed with the cap and the wires and the antenna, it's going to draw the energy in, and it's the same circuit. We're doing the same thing. This is a Joule ringer, Joule thief, Joule ringer, whatever you want to call it. When our antenna is coming out of here, it's getting fed down through here. This is the primaries in the middle of the antenna. The secondary is this coil. This is going out hitting another set of Joule ringer coils or Joule thief coil, whatever you want to call them. It's magnification of the field. Then it's going into the other circuits, and it's going, and then we get the harvest off the Magrev coils. Correct?
Correct.
Okay. And same thing.
Any comments, Cleve? We'll move the floor to Cleve.
I'm sorry, I'll mute myself.
No. I just want to agree with everything said, and just to reiterate what you said at the end, Fraz, it's cooperation, not competition. And through cooperation, we're all going to help change the planet that we know into something that it should have been for a long time. You know, like, as you say, 130 years ago, this stuff was known. And it's, through a lot of reasons that it's never come out. Most of it's greed and keeping us separated. So through cooperation, we can change it all very quickly. Thank you very much, guys.
Thank you.
Super. And anything else, Joe?
No, that's it. That's all I have to add. I'm going to stop the recording.
Okay. Thank you, everybody. We'd sure appreciate those guys that donated so far. It makes paying the bills a whole bunch easier. We're putting many, many hours to get these programs together, and dang, we sure appreciate the donations that have come in so far. Thank you much, folks.